itself affects the flow, that we'll study. But apart from that, we'll be running two different types of conditions. The first thing is we'll run a steady state simulation with inlet pressure here of 3000 pascals, but then we will try to vary the pressure using a user-defined function. And the equation that I have taken for user-defined function that corresponds to a cardiac cycle is this. So we have taken it from reference, and T is the time which dictates how the pressure is changing. So if you put T equal to 0 there, you get pressure of 791.7 pascals, okay? And then it keeps on increasing, and then it starts to decrease. So we have a pressure cycle that will be implemented here, and we'll see what happens when we have a transient pressure cycle acting on an arterial network. Now, I don't want to reiterate again the things that you can do with CFD, but we can do lots and lots of things here. For example, you can inject a drug here, inject a medicine here, and see how quickly it is spreading through the blood and at what speed it is spreading. Okay, so you can have drug delivery mechanism monitored through this. Here you can have a stent which is dispersing a given amount of drug into the bloodstream. That also you can model how effectively it will disperse it and how that will flow inside the CFD. So there are lots and lots of applications that we can do, but here I'm purely focusing on one application, is stent in an artery and how it will act. Okay, so as you have seen yesterday, the boundary conditions initially is steady flow, 3000 pascal pressure, and then we will have a UDF at the inlet. The outlet, I'm putting it at 0 pascal. As I mentioned to you, you can put any value here. You have to then increase this value just to compensate for it, because pressure is 0 gauge, it means 1 atmosphere. But in fluid, especially incompressible fluids, it is the difference of pressure that matters and not the actual pressure values, because it is incompressible and the pressure density coupling is not there. The material is blood, so we will put blood's viscosity and density, and then we will run laminar flow through this, because that is what is mostly we observe. So we will have laminar flow, steady and transient motion, outlet and blood. One thing I must emphasize again, this influence will be large. The complexity in the geometry will be large. So you can have any type of arterial network, and you can see what will be effect of stenting on that, how far a stent should be from the complex interactions, and how it will interact in a very unique manner. So this is the one. Now geometry creation, as I mentioned to you, it's a very complicated geometry, as you will notice. So what I have done is, I have given you step-by-step instructions using SolidWorks. Okay, so you can create it, but I will not go through the SolidWorks type part of creation, because I have got the, you can see links and all this is very, very complicated. It is hours and hours worth of work after which we got it created. This is the final stent that is created. This is a state-of-the-art stent, lots of links, as you can see here, allows flexibility for opening and closing, very, very rigid. So you can have rigid, and the spatial arrangement also prohibits the plaque formation and things like that. So this is the geometry. I have got the file for you, so I'll give you the file, okay, and then you can import. We are not going to create it here, because it will take you days to create it. It is fairly complicated. Unless your CAD skills are highly developed, it will be difficult for you, and I'm not sure whether we have SolidWorks here or not. So I'll give you the file. So we have, this file is a parasolid file, and then is stent x-t file, and I have got a copy. I'll give you all, you can create it. So what we do is, we create this stent using SolidWorks, and then this file is imported into Design Modeler. Okay, so this file is created. So you have asked someone, ask the manufacturer, suppose you're working on a stent with a manufacturer, ask for the CAD, save it as IGS or parasolid file, and then you can directly import into your Design Modeler. Okay, so that is what we are going to do here. Then we start the ANSYS like we did every day. Start the ANSYS, bring Fluent back here. So Fluent has come here, and then we double click on geometry, and if we double click on geometry, Design Modeler will open. a new window will open, and here first we create the display plane by clicking on the display plane icon, and once that is done, like we did every day, we change units to millimeters, and then we create the complex artery. We have discussed this in the first lecture, creation of this complex artery. So I'll very quickly rush through it because we have discussed that. Unless you have some questions on this, I'll try to go slightly rapidly on this, because this is the same carotid artery that we created last week. So we create XY plane, and on XY plane we create a circle which we extrude along the X direction, like you did all yesterday. Although we created from primitive, we created cylinder like this. Once we created a cylinder, we want to create so main thing is here we are creating we have that thing. Oh, sorry. Hey. Yeah. So like here, the strategy would be like we did last week. On XY plane, create a circle, extrude it. After extruding it, create an arc here, revolve the arc, make a hemisphere, create a plane here. On that plane create a circle, extrude it here, then create a plane and a circle here, extrude in this direction, create a line from here to here and here, create a circle and sweep the circle across this length, and finally create a sketch here and extrude a cut at this end. So this is the step that we have done on the very first week that first lecture we started. So this is exactly the same thing I am doing now here. So as I mentioned to you, this is the extrusion part. After extrusion, we create a plane, we create a hemisphere like last week. Hemisphere is created. Once this hemisphere is created, we create another plane and we join the hemisphere from this circle. So we have this extended part created here, like I just discussed. Here then we create a plane at 53 degrees and then we draw a circle and extrude it. We get this plane here. So this figure, although it looks that it is directly above it, it is the way it is being viewed. But the main artery is like this. We have plane here and this circle is being drawn here and is coming here, although it looks as if it is on top of it, like this. After this is created, so we created a circle here, extruded in this direction, and the values that are there have been calculated so that it exactly matches that part. Once it is done, we create this sketch, a straight line here and a straight line here. Then we sweep a circle along this. We go to sweep, we create this circle and we sweep this circle around this straight line and then this straight line. So once we do the sweep part, we get the final shape like this, but we want to make it sharp here. So what we do, we create a small sketch here and extrude along this so that we can cut it, and this is our final shape of the carotid artery that we have done last week. So this is our arterial bifurcation, and this is the complex junction that may affect the flow pattern here and hence affect the flow through stent as well. Any questions on this, please? We have done it on the first day itself, and I am pretty sure many of you would have made it by now, if not fully, at least to some part geometry. How many of you have completed it? The geometry part at least. No question, no answer. How much did you create? This part? Straight part. Okay, so this part is to be done. So today you can do, or maybe tomorrow you can finish this part and create this. Now the next part is more important, is putting stent in one of these. Okay, a stent has been created. I have provided you file. So let us see how do we bring a stent here inside the artery. So what we do, we freeze all this, then we go to file, we go to import external geometry file, and we choose stent x underscore t file, and we import it into the view. ZX plane is the base plane, and it has been created that if you import it like this and generate, it will be somewhere here in your, it will come somewhere in your bigger artery. Okay, so it will be coming there in the bigger artery. You will import it. Now I need to place it at a proper point. So what I have to do is I have to move it and place at the required point. So this is simple step. I will give you the geometry, just copy it, and then you can place it at a proper point. Now what we do is, after we have brought into the system, we carry out Boolean operation and unite this geometry with the artery. So we have to unite this so that it becomes one geometry. So you don't subtract, you unite it initially so that it becomes one. After that we transform it. So we go to body transformation and we rotate it. And if we rotate it by 53 degrees, you remember the arteries are at 53 degrees after the intersection. So I rotate it by 53 degrees. So when I rotate it by 53 degrees, it is aligned along one of the bifurcations, bifurcated arteries here. So what is happening? It is coming somewhere here, and I am rotating it by 53 degrees. So what happens? It is here now. It was here. Now I have rotated it by 53 degrees, it has come here. Again, it is very close to the bifurcation. So I would like to place it properly at a particular point. So I can again translate it along this direction at a proper distance. So what we do again now is we translate it till it reaches the position I want. So first translation is at minus 50.425 millimeters, and the second translation is at minus 25 millimeter, and it reaches its position perfectly. Okay. So now stent is part of the artery and it is located at a proper point. So this one artery, one bifurcation without any stent, one bifurcation with stent. These two are exactly same diameter, and we can compare the performance of the flow in this artery or in this artery. Okay. And now what we do is, because stent is a solid body, okay, and we have to model the flow around the body. In CFD, you can do it by subtracting the solid body from the flow domain. So what we have done here is, we are carrying out subtraction of this solid body from the flow domain, so that the flow can take place around the body inside the artery. So we go for Boolean operation and we subtract this stent is the tool body, the outer one is the target body, and we subtract the stent from one of the arteries. So now we have, and then we press generate. So we have now an arterial system with a complex bifurcation here. So this is very simply the geometry. This is very simple geometry. We don't have much complications beyond this. This is geometry creation. Now you can make it very complicated if you want to create a stent right from the beginning. So if you want to create some more complicated stents, you can use SolidWorks or you can use any other software. For this particular case, you can use this stent that I have created. Okay. So let us go for mesh generation now. Once the stent has been created, what I am doing is I am creating a mesh and I am giving the boundary conditions corresponding to the mesh. So we will discretize the entire flow domain into smaller volumes called mesh elements. Then we carry out the space discretization. We will create grids. In this case, we will create tetrahedral elements, although hexahedral are best, but it is easier to create tetrahedral elements. And then we will name the walls and we will supply the boundary conditions in this particular case. So if we go to mesh, you all have tried it yesterday for a single artery, most of you anyway, you know how to do it, isn't it? So this is very straightforward operation here. So we open it in the mesh and we get the geometries. We create one of the faces as inlet, so this face here will be inlet, these two faces will be outlet. So we name it as inlet, we name the other two faces as the outlets, and then we select the two legs of the bifurcation and then we hide them, and then using the box select tool we select the stent and name it as a stent. So only stent part has been named as a stent, not the arterial part. We have hidden those, and then arteries we can name it as wall. So then stent is created, walls are created, okay, and then we create mesh. So again, mesh creation is a very important part of the CFD. You have to have right mesh to get good results. So I've given some values here for the mesh sizing, and if we did that, we get a reasonable mesh which we can generate and update. You have had experience of this yesterday on a single artery, okay, single artery. Now this part also you have done, so I would like you to again, if you have any doubts, ask me. I'll go through it again. So we now click the setup and open the Fluent. As I mentioned to you, if you are running a very fast computer, you can run having more cores, you can run parallel computing, or if you don't have enough cores, then you can run serial. 3D and double precision. For higher accuracy, you can run higher double precision in this here. So Fluent will open, and now we have to define the model conditions. So as I discussed with you yesterday, we are initially running with steady state boundary conditions, steady state model, because this is steady state with constant pressure at the inlet. Later on we'll make it transient, and I'll show you how to do that. So once we have done this, then we have pressure based solver, and velocity formulation is absolute. There is no relative movement here. So that is what the general model is. Then we go to models. Which models do we use? We go to models, viscous laminar, and we use laminar model here, and we click OK. So now the condition is that flow will be laminar inside the artery, so, and that will be resolved by the laminar model. You can choose turbulence. If you have bigger systems, you can use turbulence with any of the turbulence models being used here. Then again we have to create material. So we will go to materials here. We click on this, materials, and once we click on this, we get air here. So we change from air to blood, and we give density of the blood, and we give viscosity of the blood here, and then we close it. So you will see that the material name air will be changed to blood, and then we go to the cell zone conditions, and we click on solid and add blood from the material name, so that blood is selected at every cell zone as the material, okay. So then blood will be the fluid that will be flowing through it. So this is material setup. Right, any questions up to this particular point? Any of you? Any questions? No questions, or absolutely no questions? No questions? You have done it many times, haven't we? So you all know. So let us do the boundary conditions. So in boundary conditions, we are specifying the pressure inlet. Typically it is better for incompressible flows to give one of the velocities as the boundary conditions at inlet and pressure outlet. In this case, because pressure value is known, we are using pressure boundary conditions at inlet and outlet. So at inlet I am having 3000 Pascal pressure, and outlet I am having 0 pressure. So this is steady state pressure that we are putting at inlet and outlet. Then routine solution methods, as I mentioned to you yesterday, we can choose appropriate solution methods, and then we initialize the results. So how do we initialize? As I mentioned to you, for velocities, I would not like to give 0 velocities, initial velocities. We give small velocities 0.01, and along z direction, because now my artery is along z direction, I have given a velocity of 2.41 at the inlet. This is the flow velocity, and then we can run the simulations. We give number of iterations to 100, and then we calculate we carry out the iterations, and very soon we will have the convergence. So this is the transient part. Okay, this is the transient. Sorry, this is the steady state part. Now we need to run it under transient conditions. So do you all feel you will be able to run it?
Yes, sir.
100%. Good. We'll test it. Okay, so next thing is, how do we create a UDF for the pressure signal at the inlet? So what we do is, we go to general here, and press transient. So that is the first thing that we have to do to run it. And then we go to user defined functions, interpreted, and then we browse for pin.c file, as we discussed that day with carotid. So pin.c file has the details of all the programming which is here. This is the pin.c file saved at a particular point, and you can see it is simple C+ programming, and the pressure is varying as a function of time. So what it does, it interprets this file and varies the pressure value depending upon this time. Okay, so just you have to type it on a notepad, and save it. Okay, and then when you go to user defined, access this file and go for interpretation. So what we're doing here is, yeah,
This file format will be in notepad format.
simple notepad format, free form. So just write this, create notepad, save it, and here when you go to user defined functions, here user defined, you get the file from here, source the file name, and interpret it. There are 3 options. For a very big user defined operations, there is a compiled formation as well, but for simple things we just use interpreted. But there is an option for compiling big UDFs as well. You can compile it basically. There is slightly more involved operation involving windows and all that, but for simple things it's just interpreted. Okay, any questions please? And this is the curve, this is the cardiac cycle that we are trying to implement, variation of static pressure in one pulse against time. So this is what we have written an equation, and this is the equation that is written, which this is taken from this paper, numerical analysis of atherosclerosis and aneurysm in carotid bifurcation. So this has been taken from there. So we write the equation and we write this, and then we can interpret it, and that is the only thing we have to do. Okay, that is the only thing we have to do. But now under transient simulations we have to provide some additional information, that is how close the time steps would be. Like the first time step is 0, second time step will be 0.01, 0.001 or 0.05. That is dictated by the memory you have, okay, or how big the system is. So we typically take, in this case, 0.05. Every 0.05 second, what is the flow that we are simulating? Okay, not every, but like if you're doing very complicated simulation, take 0.01, take 0.001, depending upon how closely you want to monitor the flow. So in this case, that is what is happening. And then how many number of time steps I am taking? 20 time steps, because I am simulating only 1 second of flow. I am just simulating total 1 second of flow through my arterial bifurcation. So I am taking 20 time steps. So it will run 20 simulations at every 0.05 steps, 0.05 seconds. Okay, and I am specifying the maximum iteration per time step to be 20. So for every time step we will have 20 iterations. Okay. Now for better accuracy you can have 50 or 100 or 1000 depending upon how accurate results you want. We are doing it for 20 time steps in this particular case, but you can take higher as well. And then we click on calculate. So this way you can import the transient boundary condition at the inlet and you can set the system for the transient run. Okay, any questions on this please? Like
how I see it in Fluent, whatever the time step I have given, they capture the local features of geometry. That's why we are moving to adaptive method, because we don't know about the time step size. What is the exact time step of site conversion? For the transient simulation, every cycle has to be converted. So again, we board the system in case of fixed. If we have a time step size correct, if that time step size is right for the every cycle converter, it's good. But in case I don't know what is the exact converter time steps for any particular cycle, it is what we do.
It's a bit of a problem actually. We are using CFD to understand a phenomena, but we don't know the phenomena. So what we have to do is, it's again run it initially, see what type of things you are saying, and then best thing is to reduce the time step and see whether it is changing. Keep on reducing it till it stops changing. So then you are having at least time step independence, that now your results are becoming independent of time step. That is what we do in most cases.
I see in some papers the time step that reducing it 10 to the power -5 and it's near to the micro level. Such a step don't need to time independent.
No, but like it may happen again. I assume you have done fluid mechanics at a reasonably higher level. Don't worry, I'm not going to ask any question. What happens in the fluid flow? There are many structures. Every structure have length scale and time scale. Okay, so time step. If you want to capture a phenomena, your time step should be smaller than the time scale of that particular phenomena. So suppose there is a phenomena taking place and this is the time scale for that. You try to have time scale much smaller than that time scale. Likewise, length scale is suppose known, then your mesh should be much smaller than that length scale. So this is the overall guiding line. Okay, but for macro level description of flow, macro level like reasonably big size description, time independence will be reasonably okay. But suppose if you are trying to coherent structures, you are going to do LES and all that, then this is the phenomena, then which phenomena you are looking for, and then what is the length scale and time scale for that. For big scale, you carry out the mesh independence and the time independence test, you will be reasonably okay.
In case of mesh independence, time step is size okay. We study this case, and we are running the transient simulation with the UDF. The time step size reaching to 10 to the power -5. If you are increasing the residual 10 to the power 4 to 10 to the power -5 and 6, the time steps are also decreasing or going to the macro level, 10 to the power -6 or 7.
Yeah.
In that case, there is a need of time independency because we are also running on the micro level of.
So the need will depend upon which phenomena you are trying to analyze. If your phenomena has much smaller time scale, then yes. If no, then that is fine. But if you are you PhD student, so for your thesis you will need time independence section. Otherwise, examiner will ask you afterwards to do it. So better when you submit it, do it than you doing it later.
I have done the time independence.
That's fine then.
But I didn't the reasonable answer for the fixing the time step size because at the time step size we got a 10 to the power -4. That's the average time step size we can run it. But I compare the time time step, there is a lot more difference at the local section. Because in transient case, the local section with adaptive time method have a
very small time steps here. Yes, whatever best you can have. If you have faster computers, try to have it. Your aim is to have the flow phenomena rightly mapped. So there are some guidelines on that. I think if you look at some references on how the time step size is fixed for LES, for example, if you look at large eddy scale simulation, they define a structured process to calculate the time step and the mesh step. Because you're simulating the large eddies, the small eddies you're having physical models. So there are some instructions for that. In this particular case, this is okay, whatever I've taken. Okay. Right, and then it will start calculating for each time step, and then you will start getting results for this. Now, I have just for your benefit, because you have the lecture notes, you will be having lecture notes very soon. Many students have difficulty in post-processing because you run the simulation, now what? Okay, so I have given you some instructions on that. You can create some planes on which you want to analyze the flow. Stent is already there, stent is already selected, so you can have a look at stent, what is happening on the stent. But we may need to create some planes. So for example, if you go to post processing and we go to plane, and if we check aligned with the view plane, we can create new planes on which we can see the flow, because in a three-dimensional system you would like flow to be seen on the plane. Okay, so you can create planes, and on these planes this goes through the center of the bifurcation, and you can see the flow features on this particular plane. Now, many times the students in the fluid mechanics have difficulty explaining the contours, except that this value here they see and this picture here they see. So they have difficulty explaining what is happening. Now in case of contours, the first thing you can see is that how quickly the contours are changing, okay, and in how much area these are changing. So if you look at here, this is a high pressure area dictated by P in. So P inlet is high, so you have high pressure here, but then from here the pressure is changing. So you can see that in the flow direction, how pressure is changing, that you can explain, isn't it? So you can see pressure is decreasing here, rather in a very small value from here to here, but from here to here in the two arteries, pressure is changing drastically. So pressure has decreased sufficiently in this and in this one. Now at the entrance of the bifurcation, you can see here pressure is constant radially, okay, del P over del R is 0. But if you look at here, at this bifurcation, pressure distribution is very non-uniform. So we are just doing the qualitative explanation. Quantitative explanation will come later. This is qualitative explanation, that pressure is non-uniform. Pressure in the two arterial system, one with stent and without stent, is different, and pressure is considerably low in the near stent. Your stent is somewhere here, and you can see the pressure is quite low in the stented part. And this is the qualitative explanation for this, and now we can go for the furthermore analysis. So this typically in a fluid flow, this is the first thing that you explain, the pressure distribution, because pressure distribution tells you how the pressure is, you're losing pressure, how energy is being dissipated, how total energy is decreasing in the forward direction. That's why you're losing pressure in this particular direction. Okay. So what I have done here is, I have created a number of lines, line 100, 101, and then lines 1A, 1B, 2A, 2B, 3A, 3B. So this you may have to create, and you can create a script as well for this within the Fluent. Okay, you can create a script, run a script, and these lines will be created. But in this particular case, I am doing in a systematic manner. What I am doing? I am doing analysis like this. I am creating a line through center of this artery and through center of this artery. So line 100 and 101 are the lines created along these directions in this. And then I am creating lines normal to it. And I am seeing how pressure and velocities are varying along this direction and along this direction. That would be good enough, isn't it, to tell us how systematically pressure is varying. So apart from contour, you have to have an eye, and this is where many students have difficulty, how to explain the flow phenomena. Okay, so then this way you can systematically see how pressure is changing or how velocity is changing. So let us see how it has been done. So this is how it has been created. So in the system, in Fluent, if you go to post processing, go to create, there is a line and rake, and then you can create the start point and end point coordinate of that line, and you can create start point coordinates, and you have to do some calculations. I'm pretty sure you are very good in geometry, so you can do that, and then you can create these lines in the system. You can name these lines. Now here, this can be done through a script file. Anything you can do graphically on the system, you can create a script for that. I'm not sure whether you are exposed to it or not, but this is just an option. Initially it will be difficult for you, so but you can create a script in the notepad, and then you can run, you can create a script in the Fluent, and then you can run that script file. So everything will be created. You just have to create it once, and every time it will be automatically created. But if you do it like this, then you have to do it every time or for every case and data file. Yeah.
Once we create some model, then there are many softwares which I can record that they give automatically this script version of that chemistry.
Yeah.
So suppose if we somehow let us say user defined kind of thing, if we give input or make changes in the script itself, then that effect will be shown in the model also. If we once we run this script, after making changes in the script, desired changes, can this effect can be shown in our model also?
No, model is where you are simulating a phenomena. This scripting is to display that phenomena. These are different things. You are running your model, you are carrying out flow simulation in the model. You got some results. After that results you have got, you want to display those results along some planes. So then you create some planes on this script. So it doesn't have anything on the flow calculations. It will only it will show you only the flow features afterwards in much more detailed manner. But this is very important, like those who are doing masters, or doing thesis, or may do thesis in future. This is very, very important. The analysis. Examiner wants to look at your depth of analysis. So which phenomena you want to highlight and how do you explain this is very, very important. PhD is Doctor of Philosophy. So you have to show rigorous analysis capability. Many times we hear, what are you doing? I'm doing this. Why are you doing? Don't know. So that is the problem. Just I'm doing this, that's it. But why are you doing? No question. No. So this answers why are we doing it. Okay. Here. So now you see. This is line 100 and this is line 101. So this is stented part. This is the unstented part, and we are trying to simulate the flow along the. So here I am showing static pressure on the unstented artery and the stented artery along the center line. Okay. Now you can see, if you look at this picture, there is not much different, is it? They are different, but you can't quantify it. But now when you look at this picture here, drastically different, aren't they? And that is what you wish to highlight. That is why CFD is being done. You can see in the stented artery, and it may not be the only stent effect, it may be this effect as well, the geometric effect as well, complexity, this effect as well. So you can see in the stented artery, pressure is varying quite drastically. especially in the stented region, pressure has gone very negative. Whereas in the non-stented part, especially in the stented region, pressure is reasonably constant. You can see here, pressure is although changing a bit, but is reasonably constant. But here, the change is very big. So one thing you can immediately see, stent is being exposed to very heavy pressure changes, isn't it, as compared to unstented artery. Now, one step further can be, you can remove stent from the artery and then plot onto it flow when there was no stent. In this case, this is one artery against the other artery, but you can run the simulation when there is no stent, and you can plot that figure here and see what is the effect of stent on the pressure field. Here there are two effects. One is the effect of stent, other is effect of geometry, complexity. So one stage you can go further by superimposing it on, remove the stent, run the simulation and put a line across it and see when there was no stent in the same artery how the flow was. Okay, that is one further level of sophistication which you can bring into your analysis. Is it all right? Making sense? Since we have established that in the stented region from the center of the artery pressure is changing, now I would like to see what is happening to my stent. This is a stent. This shows static pressure distribution in the stent, and as you can see near the junction here static pressure is okay, but in the stented this part static pressure has gone down because of this effect. You can see here this effect. So static pressure is reasonable, then it goes down, then it slowly picks up. So on the stent itself the static pressure is reasonable here, goes down here and picks up here. Okay, so this is how the stent elements are being exposed to pressure that you can calculate. And this pressure, if you have an FEA model, you can put this pressure into the FEA model and calculate if there is any what is the deformation of the stent elements because of the static pressure as time goes on. So that is the FEA part you can do if you are doing flow structure simulation. Okay, any question on this, please? Right, so pressure is one thing. We have now seen that pressure changes in the artery. In the stented and unstented artery pressure is difference. In the along the stent pressure is changing, that we have calculated now. Let us see what happens to velocity. Again, velocity typically, because the flow has to satisfy a very, very important condition, and you may make a note of it. No slip condition is very, very important condition. Every fluid has to satisfy. That is, the fluid velocity at the wall must be equal to wall velocity. So if wall is stationary, what will be fluid velocity here? 0. That is known as no slip condition. So velocity of flow will be 0 here, and at the center it will be maximum. So as you can see here, although it is a developing flow here, flow is developing here, and you can see velocities are higher here. And then here you can see the flow is bifurcating, and two things you must notice here. A large amount of flow is going through the outer wall. Flow goes out and it is separating here. So here you are getting very small flows, and then you are getting very high flows near the outer wall. So this flow is coming here, and in this artery velocities are becoming higher. So this is the flow development region here, and this is the flow development region here, after which flow becomes reasonably uniform. So this is the here the effect of stent can be seen, that flow is still developing afterwards. So the two main conclusions: at the center velocities are higher, where bifurcation is taking place velocity is strongly non-uniform, the separation takes place here, bulk of the flow goes through the outer wall. Okay? Is that all right? You can keep your mobile in your pocket, sir. Keep your mobile in your pocket. Is that all right? So this is the velocity profile qualitatively. That is the qualitative description. So in any research, we first describe it qualitatively and then we go to quantitatively. So here, again on those two lines, 100 and 101, you can see that in the non-stented artery, velocities are a bit higher. Okay? Whereas in the stented one, velocities are a bit lower, but a lot flatter in the stented part. This is a comparison between stented and unstented arteries. What I have done is, you remember I gave you the coordinates for 1A, 1B, 2A, 2B and all that lines. These are the lines. So I created 5 lines. Stent is from here to here. This is a stent. So I am creating similar lines on the two sides just to see how much is the difference between an stented artery and unstented artery. And you can see here at 1A and 1B there is hardly any difference. Entrance. So whatever effect you are seeing here, slight higher here, is because of this bifurcation. So this bifurcation is allowing some flow to go through this, then some flow here. Okay. But if you go to 2A and 2B, you can see in 2A and 2B the velocity profile is different. It's higher at the middle, but higher than 2B, which is unstented part. If you take 3A and 3B, the magnitudes are almost identical. 4A and 4B is higher than 4A, and 5A and 5B, 5A is much smaller than 5B. Keep in mind, this thing will include effect of both the stent as well as the bifurcation. To calculate the effect of stent only, you have to remove this stent, run the simulation, and then compare velocity profile in the two cases, and that will indicate to you what is the effect of stent on the wall shear stress and wall shear gradient. Okay, is this clear, this figure? How many of you understanding this figure? So two people understanding. No? What is this? 1A. 1A is velocity profile along this. 1B velocity profile along this. 2A, 2B, 3A, 3B. So this just shows velocity profile. I had difficulty showing all the sections in one graph. That's why I have shown this Y. Y tells us the distance from this bifurcation. Okay. So Y is the distance along this, and these are the velocity magnitudes. These are the velocity magnitudes along these sections. Okay. So this is a very useful information. Suppose if you are doing a PhD in something like this, this gives you a lot of information to all the people at one instant, isn't it? So this is what type of analysis all those who are working in fluid dynamics must be able to do. Contours are nice, but they don't give you much information. 2D plots give you lots of information. Okay. And then we calculated wall shear stress on the stent. As you can see, different parts of stent have different wall shear stress, obviously, because velocities will be different. So you can see there are some areas where wall shear stress is high, some areas where wall shear stress is low. Now where wall shear stress can be very, very low are the regions where plaque formation can take place. Okay. Where these are very, very high, that is where the wall shear stress can start affecting the blood flow or the blood composition, thrombosis and things like that can start taking place. So it gives us an idea on which are the areas where things can go a bit wrong in this particular flow situation. Okay. And then the next stage comes to modify the geometry. Can we modify stent geometry so that we have almost reasonable volume stress distribution? Can we have a stent geometry where we are not going into those regions? So that is what is our job as a biofluid experts, to design this stent in such a manner. Okay. Any question on this, please? Any questions? So this is in-depth analysis of the wall shear stress on the stent. So this is one part done. I have given you qualitative and quantitative analysis. What we have done now is we are carrying out some analysis on atherosclerosis and see how the stent with plaque formation will behave, and that we can analyze using CFD. And then we can see, can we develop a mechanism by which we can put some sort of sensor, and it tells us that, well, now this stent is not going to work properly. Right now we sense it from other biological parameters, but if there is a stent, it can directly tell us that, well, something is going wrong with me, please take care. Then we can have a look at it. So what we have done in this case is, first we are doing the parametric analysis, and what we are simulating is this is the baseline simulation that we already have done. I am increasing the pressure range baseline 0.7 times baseline, low, very high pressure in the artery. See how stent performs at all these pressure conditions, if pressure is low or pressure is very high. And I have used the same cardiac cycle as I have taken earlier with different coefficients. Is it making sense? So this is what we are going to run now for the same simulation. And now you can see here how the flow pattern changes when we have the different inlet pressure here. So this is, if 2 times the baseline pressure here, this is the baseline pressure, this is 0.7 times the baseline pressure. You can see that if P in is increasing, obviously, because we are increasing pressure here will be higher. But if you look at the bifurcation, pressure here is lower. So even though pressure is higher here, that pressure doesn't translate to the bifurcations, where pressure is seen to be lower even than the normal artery. Okay, so even though you are increasing pressure here, in the bifurcations pressures are not reaching high values. Then static pressure distribution. Here we are getting systematic trend, but slightly in the reverse order. For 2 times P in, I am seeing that along the center line the pressures are lower when P in is higher than when P in is lower. So although the nature is almost same, the velocity the profile is almost same, the pressure values are not same. They look like to be in the opposite order. Now static pressure acting on the stent, again here, if P in is higher, the first part of a stent has got lower pressure than when P in is normal or P in is lower. So static pressures are higher in these 2 cases than we are seeing in this particular case. Now here this shows the pressure variation along the stent, and you can see here in the stented part the pressure is decreasing, in the normal pressure is increasing. So this is one major deviation between a stented artery and a normal artery. You can very easily see from CFD results. So for many people, like when you all started, it looked to use CFD just as a tool to look at the flow, isn't it? But we can get lots of design information from CFD about these things. Okay. Now let us look at the velocity magnitude. Again, as the P in increases, the velocity is higher here, that is expected, and velocity is lower here, that we can see. We can see that separation point is here, separation point is here, separation point is here, that is fine. You can further see that the non-uniformity in the flow, the zone of non-uniformity is slightly higher here as compared to here and as compared to here, because velocity of flow is higher. Any disturbance will go further downstream in this particular case. So non-uniformity disturbance is higher in this particular case, we cannot see much effect of the stent at high velocity than at the low velocity. We can see the effect of stent, but here it looks almost same. So at high velocities probably we are not seeing much effect. This is the velocity profile. And why do we plot velocity profiles is because the gradient of velocity at the wall gives me wall shear stress. Isn't it? We did yesterday mu du over dy. That is why u is very important. So this is how u is varying along y, and you can see that although the pattern is almost similar, the velocity magnitudes are higher when there is p in. So we have p in here, this is along the length, this is very, very high, and these two are almost close to each other. And this is the comparison of the velocity distributions at 1a, 1b, 2a, 3a and 4a, and we can see the effect of stent on the effect of velocity on the profiles, which at the inlet there is hardly any change, but as we go further up things start to change, as you can see here. So this is where the maximum change is seen. At outlet also, here we can see maximum change here in this particular case. Then wall shear stress on stent, as you can see here, if P in is higher, areas of high wall shear stress are more predominant in case of the stent as compared to the normal baseline stent or the below baseline stent. So you can see wall shear stresses are smaller in this case, but there are areas of very high wall shear stress here in this particular case if P in is higher. So high blood pressure may have significant influence. So if you don't manage your blood pressure, it may have significant influence on the performance of the stent in the body. Okay. So this shows in a quantitative form. Again, this is an example. The wall shear stress, how it is changing if the P in is changing. So if P in over P baseline is 0.75, that is P baseline is higher than the P inlet, then we have this wall shear stress. But as we reach 1, that is fine. As the P in is increasing over the baseline pressure, the wall shear stress is increasing drastically, and that is not a good news if wall shear stress is increasing drastically as we get along. This is the average wall shear stress over the entire stent, and this is how the local wall shear stress starts to increase at a particular point in the stent. Okay. Any question on this thing? Any questions, please? So not only we are able to simulate the flow, we are able to get the quantities that tell us about the performance of a stent in a particular case. Okay. So this is what this is again not only wall shear stress, rate of change of wall shear stress along the artery is also a very important parameter, and so change of wall shear stress in this particular case, as we can see, as P in is increasing, the gradient initially decreases, then increases, and then monotonically it starts to increase further, which again may not be a good news, because that indicates how fast wall shear stress is increasing or decreasing. There are some other parameters. Ultimately, stent is an obstruction to the flow. Okay, so separation of flow may take place. So what we have calculated here is the vorticity, because the three-dimensionality of the flow caused by the stent, and it is much higher when the inlet pressure is very high. It's okay at the baseline condition, and it is very small at the low condition. The positive QQ criteria, again, as I mentioned to you in the last class, this is the half of square of the vorticity magnitude minus the strain rate. So if it is positive, it means the vorticity magnitude is more than the strain rate. So there is more rotation as compared to deformation. And so this shows again the areas of more vorticity in the case of baseline and the low as compared to the high P in, because here you can see lots of whites. Here these are largely blue in this particular case. Okay. This is how we carry out the performance analysis of a stent. So take one shape, based on these criteria, modify the design. Look at it again, modify the design again. Look at it again, small changes, and then you can reach an optimal design of stent. Okay, which stent will work in which manner. Okay, so this is the design part. Now next part is, how do we develop a smart stent? How can we develop a smart stent that can tell us that things are going to get worse? If you wish, you can have 5 minutes break and come back for 5 minutes. Okay, and then we can start on this, because this will go for some time, so you can take 5 minutes break if you wish.